lesson 9.3, sequences. In the next lesson, we're going to talk about series, which is based off of sequences. Later in this lesson, we'll talk about this dude, which is Leonardo of Pisa. So what we're going to focus on in this lesson: infinite sequences, limits of infinite sequences, and then arithmetic and geometric sequences. We're not going to focus so much on the graphing aspect in this lesson. Okay, the reason we're going to learn this, for those of you that take calculus, when we're dealing with finite limits, those are going to be involved next year when you take that class. Many things we study in mathematics follow a general pattern. Okay, sequence is another one of those items. Basically, it's an ordered progression of numbers that typically follows a pattern that we can recognize. There's two main types of sequences. We have a finite sequence, which means it has a fixed number of terms. It will come to an end. There's also an infinite sequence, which means the number of terms continues on, it never comes to an end. For our sake, we're going to deal and focus with sequences that follow a general rule. They have a pattern that we can determine that allows us to find any given term in that sequence. Okay? There are some sequences that do not follow a general pattern, though. Next, we need to discuss the limit of a sequence. Okay, so suppose we let a sub n be the sequence of real numbers, and we're going to consider the limit as n approaches infinity of a sub n. If we calculate that limit and it is a finite number, then the sequence converges. If we calculate the limit and it approaches infinity or is non-existent, then the sequence diverges. Our first example, finding limits of sequences. Determine whether the sequence converges or diverges. If it converges, then give the limit. Okay, so we need to take the limit as n approaches infinity of our sequence, which is defined as 2 divided by n. Okay, we're going to use what's simply called the direct substitution method. We'll learn more about this for those of you that take calculus. But all we really have to do is take 2 divided by infinity. Okay? So we want to think of infinity, it's a concept, it's referring to numbers getting increasingly large. So if we have 2 divided by a very large number, and that number is just going to increase, well, 2 divided by a large number is going to be very small, and it's going to approach a value of 0. So the sequence converges, and the limit of this sequence is equal to 0. We talked earlier about sequences either being finite or infinite. We can also distinguish sequences between being arithmetic or geometric. Arithmetic sequences occur when we have a common difference, meaning we're adding the same value to consecutive terms. The general way we're going to write this is a sub n is equal to a sub 1, which stands for our first term, plus n minus 1 times d, where d stands for that common difference between consecutive terms. If you look down below, we have another formula. That is the recursive formula. The formula we talked about above is called an explicit formula. Okay. A recursive formula, basically you're adding the common difference to the previous term, and the explicit formula would be more of a linear equation. You're multiplying by the common difference. So now we're going to go through an arithmetic sequence. For part A, we want to find the common difference. So our sequence, we have -2, 1, 4, 7. This is an infinite sequence. We can tell that by the ellipses, the 3 dots at the end. That means this is going to continue on and on, so it's infinite. Part A, we want to find the common difference, the pattern for this arithmetic sequence. To go from -2 to 1, we would add a value of 3. To go from 1 to 4, we're adding 3. So our common difference, that d value, is 3. For part B, we want to find the 10th term of the sequence. So we're looking for a sub 10. We can use that explicit formula we talked about on the last slide. A sub 10 is equal to a sub 1, which our first term is negative 2, plus n minus 1. In this case, our n value is 10 minus 1 times the common difference, which is 3. So now if we go through that, 10 minus 1 is 9. 9 times 3 is 27. 27 plus negative 2, we get a value of 25. Now for part C, we want to write the recursive rule for the nth term. When writing the recursive rule, the first thing we need to do is write down our a sub 1 value, the first term in our sequence, which is negative 2 in this case. Now for the recursive rule, we have a sub n is equal to a sub n minus 1 plus our common difference, which is 3 in this case. Another extra thing we need to have when talking about the recursive rule is stating for which n values we're working with. In this case, to make this true for our given sequence, we have to start our n value at greater than or equal to 2. Okay, I know that's a little confusing, so if you have questions on that last portion, make sure to ask me. Now for part D, we're looking for the explicit rule for the sequence. So we have a sub n is equal to a sub 1, which in this case is negative 2, plus n minus 1 times our common difference, which is 3. So if we simplify, use the distributive property, we have negative 2 plus 3n minus 3. Now we just have one more part to simplify, combine like terms. We get 3n minus 5. Just a quick review of this problem. In part A, we found the common difference of 3. In part B, we found the 10th term in the sequence. In part C, we found the recursive rule for the nth term. And then in part D, we found the explicit rule for this arithmetic sequence. Now we're going to discuss geometric sequences. If we're looking at one term to the next term, we can tell it's a geometric sequence because we're multiplying by the same value each time. We use the variable r to refer to that value, which is called the common ratio. So a sub n is going to be equal to a sub 1 times r to the n minus 1 power. That is the explicit rule for a geometric sequence. If you look down below, we also have one for the recursive rule, which is going to be a sub n is equal to a sub n minus 1, the previous term, times r, which is the common ratio. In this example, we have the infinite sequence 2, 6, 18. This is going to be a geometric sequence because we're multiplying by the same value each time. So for part A, we want to determine the common ratio. What value are we multiplying by each time? So we get r is equal to 3. Part B, we want to find the 10th term in the sequence. So a sub 10 is going to be equal to a sub 1, which is 2, times our common ratio raised to the n minus 1 power. So 10 minus 1 would be 9. So if you multiply that out, you get 39,366. For part C, we want to write the recursive rule. Again, we have to make sure we write down what our first term in the sequence, a sub 1 is equal to 2. And then we get a sub n is equal to our common ratio, which is 3, times a to the n minus 1, where n is greater than or equal to 2. Again, talk to me if that last part is somewhat confusing to you. For part D, now we're going to write the explicit rule for the nth term. So we have a sub n is equal to a sub 1, which is our first term, which is 2, times our common ratio, which is 3, raised to the n minus 1 power. So first in part A, we found our common ratio, which was 3. Part B, we found the 10th term in the sequence. Part C, found a recursive rule for the nth term. And part D, found an explicit rule for the nth term. The last part to discuss is a special sequence you've all heard about, the Fibonacci sequence, and that can be defined cursively by a sub 1 is equal to 1, a sub 2 is equal to 1, and then our recursive rule is a sub n is equal to a sub n minus 2 plus a sub n minus 1. So we're adding the previous two terms together in order to get the current term. And this is true for all positive integers, n greater than or equal to 3. Okay, that person you saw the picture of at the beginning of the slide, that is Leonardo of Pisa. He is actually referred to as Fibonacci. He wrote and did his mathematics under the name Fibonacci, thus where we get the name, the Fibonacci sequence, named after him.